Hello, my name is Miko Rianggawarus, NVM G1D021065 from class A. The first term in this expansion vanished because we are integrating around a circle. This is just a replication of the fact that there are no magnetic manifolds. For the second term, there's a way to write it in slightly more manageable form. To see this, let's introduce an arbitrary constant vector g and use this to look at. Integral from c dx action times g in bracket r times r action. Recall that from the point of view of this integral, both g and r are constant vectors. It's the vector r action that we integrating over. This is now the kind of line integral of a vector that allows us to use Stokes' theorem. We have integral from c dx action times g in bracket r times r action equal integral from s ds times delta times in bracket g in bracket r times r action in bracket equal integral s ds e element epsilon e jk rho action g in bracket gk re r action e, where in the final equality we restored to index notation to help us remember what's connected to what. Now the derivative rho action acts only on the r action, and we get integral from c dx action times g in bracket r times r action equal integral from s ds e element e jk g k rj equal g times integral from s ds times r. But this is true for all constant vector g, which means that it must also hold as a vector identity. Once we strip away g, we have integral from c dx action in bracket r times r action equal s times r, where we have introduced the vector area S of the surface as bounded by C, defined as S equal integral S ds, integral from S ds. If the boundary C lies in a plane as it does for use, then the vector S point out of the plane. Now let's apply this result to our vector potential. With the integral over r action, we can treat r as the constant vector g that we introduced in the lemma. With the first term vanishing, we're left with a in bracket r equal mu 0 all over 4v times m times r all over r cubed, where we introduce the magnetic dipole moment m equal e times s. This is our final simple answer for the long range. Before of the vector potential due to a current loop. It remains only to cover the magnetic field a little algebra gives. B.R equal mu0 all over 4v in brackets 3 in brackets m times vector r kurang m all over r3 in. Now we see why m is called the magnetic dipole. This form of the magnetic field is actually the same as the dipole electric field. I stress that the V field due to a current loop and A field due to two chains don't look the same close up, but the identical dipole Lorentz fall of 3.3.2 general current distribution. We can now perform the same kind of expansion for a general current distribution G localized within some region of space. We use the Taylor expansion in the general form of the vector potential. A E in bracket R equal mu0 all over 4v integral d qubit times r action G E time in bracket r action all over r kurang r action sama dengan equal mu0 all over 4v integral d qubit r times r action in bracket G E in bracket r action all over r plus G1 in bracket r action times in bracket r times r action all over r3 plus dan seterusnya, where we using a combination of vector and index notation to help remember how the indices on the left and right hand sides made up. The first term about vanish heuristically. This is because current can stop and end. They have to go round in loops. This means that the contribution from one part must be conquered by the current somewhere else. To see this mathematically, we use the slide out identity. Rho G in bracket G times RE equal in bracket rho G R1 the plus G1 equal G1, where the last equality flows from the continuity condition delta times G equal 0. Using this, we see that the first term in is a total derivative in bracket of rho all over rho r action E rather than rho all over rho RE, which vanishes if we take the integral over R3 R qubit and keep the current localized within some interior region. For the second term in bracket, we are similar trick now with the identity. Rho G in bracket G R E R K equal in bracket G times G in bracket RERK plus GERK plus GKRI equal JERK plus GKRI. Because G in is a function of R action, we actually need to apply this trick to the GER action. G term in the expression. We once again abandon the boundary terms to infinity. Thank you.